Climate scenario analysis is a forward-looking analytical process used to evaluate how different climate-related futures may affect organizations, assets, portfolios, and economic systems. Unlike traditional risk assessment methods that rely heavily on historical data, scenario analysis examines a range of plausible future climate pathways characterized by varying levels of emissions, policy responses, technological developments, and physical climate impacts. Organizations use scenario analysis to identify vulnerabilities, assess resilience, evaluate strategic options, and support decision-making under uncertainty. Financial institutions, corporations, regulators, and investors increasingly employ climate scenarios to understand potential exposure to physical and transition risks across different time horizons and economic conditions. Organizations apply climate scenario analysis in multiple areas of risk management and strategic planning. Companies use scenarios to assess how climate-related risks and opportunities may influence operations, supply chains, capital expenditures, business models, and long-term competitiveness. Financial institutions evaluate the potential effects of climate scenarios on lending portfolios, investments, insurance exposures, and capital adequacy. Scenario analysis supports governance processes by helping management and boards understand the implications of alternative climate futures. It also assists organizations in developing adaptation and mitigation strategies, prioritizing investments, stress testing assumptions, and enhancing disclosure practices consistent with climate-related reporting expectations. Global net zero scenarios describe pathways in which greenhouse gas emissions released into the atmosphere are balanced by greenhouse gas removals, resulting in net zero emissions. These scenarios are central to international climate objectives because stabilizing global temperatures requires limiting the accumulation of greenhouse gases in the atmosphere. Net zero pathways generally involve substantial reductions in emissions across energy, transportation, industry, agriculture, and land use sectors. However, many scenarios recognize that some residual emissions may remain difficult to eliminate completely. As a result, carbon removal processes play an increasingly important role in achieving net zero outcomes and meeting long-term climate stabilization goals. Carbon removal processes are designed to remove carbon dioxide from the atmosphere and store it over extended periods. Examples include afforestation and reforestation, improved land management practices, bioenergy with carbon capture and storage (BCCS), direct air capture technologies, and enhanced weathering approaches. Many net zero scenarios assume significant deployment of carbon removal methods during the second half of the century to offset residual emissions from hard-to-abate sectors. However, these approaches present challenges related to cost, scalability, technological maturity, land use, environmental impacts, and governance. Consequently, most climate pathways emphasize aggressive emissions reductions alongside carbon removal rather than relying exclusively on negative emissions technologies. The Intergovernmental Panel on Climate Change, IPCC, uses standardized scenarios to evaluate potential future climate outcomes. Representative concentration pathways, RCPs, describe alternative greenhouse gas concentration trajectories and associated levels of radiative forcing by the year 2100. Lower emissions pathways correspond to stronger climate mitigation efforts and lower levels of warming, while higher emissions pathways reflect continued emissions growth and greater climate impacts. RCPs provide a common framework for climate modeling and impact assessment. These pathways allow researchers, policymakers, investors, and organizations to compare climate outcomes under different emissions assumptions and evaluate potential physical and transition risks. Shared socioeconomic pathways, SSPs, complement RCPs by describing alternative socioeconomic futures that influence emissions, adaptation capacity, and climate policy responses. SSPs examine factors such as population growth, economic development, technological progress, inequality, governance, education, and resource use. Different SSPs represent varying levels of challenges associated with climate mitigation and adaptation. When combined with RCPs, SSPs provide a comprehensive framework for analyzing interactions between socioeconomic development and climate outcomes. These integrated scenarios are widely used in climate risk assessments, financial analyses, policy evaluations, and corporate planning because they help organizations understand the range of plausible futures that may shape climate-related risks and opportunities.